Okay, so let's start, right? So last class we had seen a few models, Thomson's model. Then we saw about the cathode ray discharge tube and a few more models. Okay. So in today's class we will basically focus on the wave nature. Okay, and the different like parameters of the wave nature. So before that, coming on to the Bohr's model, right? There were two main factors, okay, which resulted in Bohr's model. One is the dual nature of the atom. Dual nature meaning the previous theory said that a atom can have wave nature as well as particle nature, okay. So because of that, the dual nature of atom, okay, because it can have both. That is the particle nature as well as wave nature, okay. And the second one is atomic spectra, okay. So you will study the atomic spectra in detail when we will do the hydrogen spectra. Okay. But just for now, you'll have to remember the 2 points. One, what led to the Bohr's model is one is the dual nature of the atom, that is the particle nature and the wave nature. And the second one is atomic spectra. Okay. So now, besides that, Maxwell, he was a scientist who entirely proposed the wave nature, okay, of the atom. He basically studied on the wave nature, like the wave properties. Okay. So, so what he studied basically was he studied the interaction of the particles with the electric and magnetic field. Okay. Like what happens when you keep an atom in the presence of magnetic and electric field. This Maxwell proposed. Okay. So now we will start with the wave nature. Okay. So, okay. So this is a wave. Okay. So, when we study the wave nature, we consider the atom, we keep the atom in the presence of magnetic and electric field. Okay. So you all have to imagine that, like there is electric and magnetic field which is perpendicular to this wave. Okay. So speaking about the waves, now this point, okay, the top most point is called the crest. Okay. And what is the down trough? Okay. So all have heard, like you all have a basic idea about the wave, right? The top is called the crest and the down, this point is called as the trough. Okay. Then what will be this? Like the height of the wave is called the amplitude. Okay. Amplitude, like suppose if I see height of the wave, it represents the amplitude. Okay. Amplitude is nothing but the height. So now the first parameter, let us discuss each parameter in detail. Okay. So first one is wavelength. So what do you all understand by wavelength? Do you all have any idea about? Yeah. So wavelength is nothing but the distance between two consecutive crests or two consecutive trough. Okay. So this is given by lambda. Okay. So basically, first one is wavelength. Okay. We represent wavelength terms of lambda. Symbol for wavelength is lambda. Okay. So it is not wavelength is nothing but the distance between two consecutive crests or two consecutive trough. Okay. Then like there are a few conversions. Okay. Like you'll have to again. Last time also it happened the same thing, and then by mistake in a hurry, I tapped on that schedule now thing, and then it went off. So this time I just set that schedule later on. So yeah. So yeah, I was talking about wavelength. So when I speak about wavelength, wavelength is the distance between two consecutive crests of two consecutive trough. Okay. So when we study about wavelength, there are few conversions which you all have to remember. Okay, like when you all solve any numericals or any problems. So first one you all have to know is 1 Armstrong will be equal to, any idea? 10 raised to minus 10 meters. If I want to write in terms of centimeters, then 10 raised to minus 8, okay, centimeters. And we can also like write wavelength in terms of nanometers. So 1 nanometer will be equal to 10 raised to minus 9 meters, okay, and so on. We also can write in terms of centimeters, but mostly preferred are meters, nanometers. And suppose if something is given in Armstrong, then we have to convert it in terms of meters. Okay. So now next parameter is frequency. Frequency we represent in terms of mu. Okay. So frequency is nothing but the number of waves which pass through a given point in a second is called a frequency. Suppose if I consider this as my point. Okay. So I want to find, like, how many waves, like this will be one wave, right? From here to here. Okay. So frequency is nothing but the number of waves will pass through a particular point in 1 second. Okay. That will be my frequency. So with frequency, the symbol for frequency is and sorry, and we write in terms of hertz. Okay. We write frequency in terms of hertz. So basically 1 hertz will be second inverse. Okay. So suppose if I have, like, like you all will know the importance when we start solving problems. Okay. Suppose if I want to cancel something, right? Like I want to cancel. Suppose if I have some number here, if I have, say, some second inverse, okay, and down I have hertz. Okay. So this conversion will be important when I solve a particular problem. Okay. In the problem, whether if I want to cancel a particular entity, okay. So suppose if I write hertz in terms of second inverse, then it will be easy for me to cancel out, right? So for that purpose, you'll have to know 1 hertz is equal to second inverse, okay? And it also can be, you also can write in terms of like kilohertz. So kilohertz is nothing but kilo is 10 raised to 3 hertz, okay? So on. Then the third one is speed, okay? Like the velocity. So what do you all understand by the term velocity? Heard about this term? Velocity is nothing but the speed of light. Third one is velocity. Okay, is nothing but the speed of light. Okay, so when we speak about velocity, right, the speed of light in most of the cases it will be the same. Okay, we represent this in terms of we write in terms of meters per second. Okay, but like we write C. You all must have heard, right? C. You all will not have any problems earlier in your 10th standard and all. Like you all do not study this term. Okay, so C we write in terms of 3 into 10 raised to 8 meters per second. Okay. And suppose if I want to write in terms of centimeters per second, then it will be 10 raised to 10. Okay. Just a note that this 10 raised to 8 is positive here. Okay. Because many a times, like, like in a hurry, we tend to write 10 raised to minus 8. Okay. These all things, right? Like nanometers, then Armstrong, those are like, the numbers which are raised to that particular power will be negatives. Okay. But here, when we speak about speed of light, right? That 10 raised to 8 will be positive. Okay. Then the fourth one is wave number. We write in terms of mu dash, mu and then a dash on top. Okay. So wave number is nothing but the opposite of wavelength. Okay. So we can write wave number in terms of 1 upon lambda. The reciprocal of your wavelength will be your wave number. So that is given by 1 upon lambda. Okay. And there is another formula which is very, very important one, that is C is equal to lambda nu. Okay. So basically this formula and this formula, they both are very important, okay, when it comes to problems. The fifth one will be amplitude. Amplitude is nothing but the height, okay, of that particular wave. From this point to the crest, it is called the amplitude. You can consider this also as the amplitude from this point to the trough. All I've understood this 5 terms. Any doubts? Okay. So if you all have understood this, let us move on to electromagnetic spectrum. Okay. So I think on page 8, if you all have your notes, right? On page 8, like I have drawn the spectrum. Okay. So first, starting from gamma rays, then we have X rays, then we have UV, then IR, microwaves, and the last one is radio wave. Okay. So we have 7 types of rays. Okay. First is gamma, then is X-rays, UV, visible, IR, microwaves, and radio waves. Okay, 7. So you'll have to know, like, like suppose if we consider this region, right? This is further divided into your spectrum, like the 7. Like we use the term VIBGYOR, right? So your visible is divided into this VIBGYOR. Violet, indigo, blue, green, yellow, orange, red. Okay. So if I speak about the frequency and wavelength in terms of this spectra, okay, the frequency decreases, okay, as we move from X-rays to your radio waves, okay. So the frequency will decrease. And suppose if I speak about the wavelength, should the wavelength increase or it should decrease? Why increase? Yes, we know this formula, right? C is equal to lambda nu. So suppose if I want to find one particular parameter, okay, here if I consider the wavelength, so I will keep the wavelength on one side and I will move the other parameters on the other side. Suppose if I do that, I will get C by nu. Okay. So suppose if I take this particular formula, okay, then you know that suppose if the wavelength increases, the frequency should decrease because they are inversely proportional to each other. Okay. If one parameter increases, the other one should decrease. So suppose no, if the frequency decreases in this order, okay, from gamma rays to your radio waves, it decreases the frequency. So since the frequency decreases, the wavelength should increase, right? So the wavelength increases. Okay, so this is very important. Like you all have to remember in this order only. In this order. Meaning like you all shouldn't like jumble up, okay? Or starting from gamma ending to radio waves, okay? It is fixed, like the order is fixed. So suppose if I ask you all a question, if I consider two things, okay? If I consider IR, that is infrared, and if I consider X-rays, okay, which will have a higher frequency, IR or X-rays, which will have a higher frequency? Think properly and tell. X-rays, right? Why is that IR? Okay. Because the frequency decreases. So if I say something decreases, then this side it will be higher and that side it will be lesser, right? Okay. Suppose if I consider UV and if I consider microwave, which will have a higher wavelength? If I consider UV and if I consider microwave, wavelength, yeah. Microwaves, okay? So how confusing it can be. So for that, like, now I have all these terms, like I have written all this on the board. It becomes easier for you all to compare and tell me, like, which is, which will have a higher frequency, which will have lesser. But in case if I would have rubbed this part, okay, and you all would have just like, if you all would have studied it, then it becomes a bit like difficult, like it becomes confusing, like you tend to think, okay. So for that, in case like many textbooks, okay, like I have given this in my notes, but many textbooks or like many other books like will have the other order, like they will have gamma rays this side and radio waves towards the left, okay. So then it becomes a problem. So what you'll have to do is, if you all are following one order, right, you'll have to stick to one order only, okay. So x-rays, sorry, gamma rays, and last will be radio waves. Okay. If you all are following this order. And this order will also be the same, like starting from violet and the last will be red. Okay. If you all twist the whole thing, right? Like if you all get radio waves towards the left and the gamma rays towards the right, this part also will shift. Okay. Red will come here, violet will go towards the right. Understanding? So you'll have to follow, or you'll have to memorize this thing. It is important. But I have also mentioned like the values, like 10 raised to 24, 10 raised to 18 and all. Okay. Those like y'all, I won't advise you all like to, like study, but in case if your teacher has told you all, to study that thing, then you all have to study. Okay. But main thing is to know the sequence. Any questions? Okay, suppose if I ask green and orange, which will have a higher frequency? Yellow or violet? Which will have a higher wavelength? Yellow, violet. Yellow, right? Understanding? Hmm? Red will have the highest wavelength. Yeah. Because of that, we have those signals and all those red, right? Why? Because it has a higher wavelength. So it is like it becomes easier to see from far distance because of the higher wavelength of red. Okay? Yeah. Yes, I think this you all do not have, right, in your 10th standard. Only like this you all studied the white light, which splits into 7 colors. Okay. So yeah. Any doubts? If you all have no doubts, then I want you all to try to solve question 6. Try solving question 6. Which formula will you use? C is equal to lambda mu. So what will be C? 3 into 10 raised to 8. Okay. And what will be the frequency? 1368 into 10 raised to 3 hertz. But I have said hertz, you also can write in terms of second inverse. Okay. So suppose if I write hertz in terms of second inverse, it will be hertz, which is converted to, or I wrote it in the form of second inverse. Okay. This second inverse gets cancelled. So what will remain is 5. So the answer will be 219 meters. Okay. Huh? Okay, sorry. 456. So 1 divided by 456. 6 size 18. So basically, you'll have to solve using logs. Okay. Or if you all can avoid, then you all can also like divide. Basically, it will be 1 upon 456. Okay. And this will be 10 raised to 8 into raised to minus 3. So it will be whatever answer you get, this into 10 raised to 5. Right? Any doubts? Easy, right? So you all can take the 7th and 8th one for homework. Seventh and 8th one. Okay. So if you all are done solving that problem, you can take the 7th and 8th one for homework. Okay, like it's very simple, right? It is direct substitution of the values into the formula, right? Okay, so next one is the drawbacks of the wave theory. Okay. So what was seen that the wave nature of light, it could only explain the diffraction and interference. Okay. So what do you all understand by interference? The term interference. Okay. So interference, okay, in terms of our chemistry, most to be more specific in terms of wave nature, interference is when we have two waves, okay? When we have two waves and they add on, okay? Like we say, basically these two waves will add on to give you a wave of a higher amplitude. Okay, so this will add on, like the crest will get added to the crest, trough to the trough, and it will add on. Since it adds on, like the amplitude will increase. Okay, similarly, we have something constructive interference, and this is further on. Okay, so you all don't have to that depth. Okay, you all just, in fact, like you all don't even have interference, but it is just given that the wave nature of light, it could explain the two phenomena. Okay. First one is interference and the other one is diffraction. You all have got the term interference, right? Interference is like the two waves will combine and give you a new wave which will have a higher amplitude. Okay. Height. Basically, amplitude is nothing but height. Coming on to diffraction is something, if I have a light, okay, a source of light, if I pass it through, say, a object, okay, when I pass it through an object, the light, it will bend, okay, it will change its direction and it will bend, okay. So basically, the bending of the light is called as diffraction, okay. So basically, it says that the wave nature could explain diffraction and interference. Okay. But now we will see what are the drawbacks. Okay. It says first one is the nature of emission of the radiation from hot bodies. Okay. It could not explain like the radiation, like the emission. Like suppose if a particular body or if say a object is very hot, okay, it will tend to give out some radiation, right? If it is very hot. This particular concept was not explained by the wave nature. Okay. Secondly, the injection of the electrons from the metal surface when something strikes it. Like suppose if a radiation strikes, suppose if I have a metal, okay, and if some radiation strikes this metal surface, okay, it will have some energy, some frequency, right? So when it strikes a particular surface, it was expected, like, some of the electrons will be given out, okay, when this particular radiation strikes the metal surface. But this was not explained by the wave nature. Okay, so second drawback was this. The third one was variation of heat capacity of solids. Okay, so basically, why heat capacity? Like suppose heat capacity is nothing but the temperature which you supply to any object in order to increase that particular temperature of that object. Suppose if I have, suppose if I have this board, okay, the whiteboard. If I want like to increase the temperature of this, okay, to increase the temperature of this whiteboard, some amount of heat will be required. So basically, the amount of heat which is required to increase any object's temperature is called as heat capacity, okay. So this phenomenon, like this thing also wasn't explained by your wave nature, okay. The third one. The fourth one is the line spectra of atoms with reference to hydrogen. Okay. So, especially in Bohr's model of atom, right? He focuses entirely on hydrogen. Like there are different, like your Balmer series, Paschen, and so on. So that will come further on. So now you'll just have to remember that the spectral line spectra of the atom also was not explained by the wave nature. Okay. So these four drawbacks you'll have to know. Understood? She's not feeling well. Not feeling well. Do one thing, just go and splash water and come in. Sure? Drink some water again. Okay. Done. So these were the four drawbacks. Okay. Then further on, like now we are done with the wave theory. Okay. Wave nature. Okay. So basically, who had proposed wave nature? Maxwell had proposed wave nature. Okay, so Maxwell, he entirely studied on the concept of wave nature. Okay, like the different parameters like frequency, amplitude, and wavelength. Everything he studied. Then further on, there were some drawbacks to his theory also. Like the wave nature also had some drawbacks. So since it has some drawbacks, this theory was not ideal. Okay, like to propose the atom. Okay, so further on there were particle. Okay, like studies on the particles. So then the particle nature also came into picture, like the studies based on that. So Planck, Max Planck, he basically studied on the particle nature of the atom. Okay, so Planck's quantum theory. Okay, so this theory, it entirely will focus on your particle nature. Okay, so what he said or what he proposed is when a radiant energy which is emitted or absorbed by any body is not continuous, okay, but it will be discontinuous in the form of small packets of energy called as quanta. So what he said is when a particular body, okay, or when a particular object will emit or it will absorb light, okay, that particular emission or absorption, it won't be continuous. Okay, that particular body, it won't be continuously like able to, give out energy or say absorb energy. Okay, it will do in the presence of small packets of energy. Okay, it won't be continuous. It won't be it. In other words, it won't continuously give out energy. Okay, or take in energy. It will do this particular thing by small packets of energy which are called quanta, like small portions. Okay, so basically, quanta is nothing but a plural name, okay, for energy. Okay, suppose if we say quantum, quantum refers to singular, one. Okay, quanta will be many. Plural form of quantum is quanta, many. Okay, so basically, what Planck said is that when a particular object will emit or absorb a particular radiation, it will do in a discontinuous fashion. Okay, like it will do in the form of small packets of energy, which are called quantum. Okay, so then he also he gave this equation. Okay, E is equal to H nu. He said energy. He said that energy will be directly proportional to your frequency. Okay. Since now I want to get rid of this directly proportional wala sign, right? I introduce H, which is a constant, Planck constant. Okay. So H will be nothing but 6.62 into 10 raised to minus 34 joule second. Okay. So this is another important formula. Okay. First, you all have marked those two formulas, right, on your notes. When I say particular, those two formulas are important. Just like you all can do or just put a star or just write important or make a box there. Okay. Otherwise, like if you all can, like specially write all the formulas, like now the first chapter has got over, right? So what you all can do is make like a chart in which all the formulas are on one page only. Okay, like from the start to the end, like we saw the first chapter, we saw like different formulas when it comes to temperature. We saw Kelvin, Fahrenheit, and all, right? So you all can write all the formulas on one paper, do a chart, which will help you all only. Okay, so one chapter, all the formulas on one page. Okay, same way for the second chapter also, you all can do the same thing. Okay. So first one, so far this I feel is a third one, right? First one that C is equal to lambda nu. Then the second one was wave number is inversely proportional to your wave length. Okay. So mu dash is equal to 1 upon lambda. That was the second one. And this is the third one. E is equal to H nu. Okay. E is nothing but your energy and mu is your frequency. Okay. So suppose if I want to write this equation in terms of my wavelength, how will I write? If I want to write this in terms of wavelength, hmm, how will I write? Hmm? Right. This substitute frequency, right? Easy. So E is equal to H. U will be what? C by lambda. Okay. So it depends like what you are asked, and it depends on the questions also. See, one formula, like I have this one formula which I can write in terms of 1, 2. Suppose if I want wave number, then how will I write? Will be E, H, C, like this, right? So the like this is not mentioned, but I'm just saying, see the possibility of the examiner or the teacher asking the question. Okay, you all like this was the simple form of that. E is equal to H nu. Okay, from this you can write this formula. From this you can also write this when you have the wave number. When you have the wavelength, you can also write wavelength in terms of wave number, right? I have said that wave length is inversely proportional to your wave number, right? So one formula, but three different forms of it. Because what normally happens is when a particular question is asked, right, and it says like if you're given the energy, okay, and Planck constant, so you'll know only. But if say the wave number and all is asked, you tend to, like think at times a lot, or like, like this thing was not thought. But everything is thought, you just have to apply. Okay, so I think I have not included that. So you can just make a note like of it there. Okay, you can also write in terms of wave number. Done? Yes, so next concept is photoelectric effect. Okay, so what is photoelectric effect? When a radiation of a minimum frequency, when it strikes a metal surface, okay? Like suppose if I have my metal surface, okay? Suppose if a radiation of say minimum frequency, okay? Sorry, of a minimum frequency will strike this metal surface, right? Some amount of electrons will be given out, okay? So basically this concept, okay, of the radiation of a minimum frequency striking this metal surface, and due to the striking of this metal surface, some electrons will be thrown out or given out. It is called photoelectric effect, okay? Understood? When a minimum frequency of any radiation strikes a particular metal surface, some amount of electrons due to the striking of that metal, due to the radiation, right? It will strike this metal surface, and due to which some amount of electrons will be given out. This phenomenon is called as photoelectric effect. Okay. Now, when I talk about the minimum frequency, right? The minimum frequency, it is also called as the threshold frequency. Okay. Threshold frequency. Threshold frequency is nothing but the minimum frequency with which the radiation will strike the metal surface. Okay. Okay. And there is another term that is stopping potential. Stopping potential is nothing but the minimum potential at which the current will be zero. Okay. I have no place to write it. Stopping potential This will be the minimum potential with which the current will be zero. Okay, so we learned three concepts. One is the photoelectric effect. It is nothing but when a radiation of minimum frequency strikes the metal surface, some amount of electrons are given out. This particular concept is called as the photoelectric effect. Second one, we studied the threshold frequency. Frequency is nothing but the minimum frequency with which the radiation will strike this metal surface, okay, or the metal object. The third one, we studied about the stopping potential. Stopping potential is the minimum potential when the current will be zero. Minimum potential. Stopping potential. It is like it is given that the minimum potential at which the plate's photoelectric current will be zero. Like this is more into, if you want to really study, then you have to go into the depths of that. It is more sort of physics concept, okay? But in chemistry, what is important is just the terms, okay? Like what is stopping potential? So stopping potential is basically like, see, when you hear the word stopping potential, meaning something which is required to stop, right? The particular, like the flow, something like that. But the minimum flow or the minimum potential which you apply when the current will be zero, meaning no current will pass through that. If no current passes through that, meaning no electrons will be given out, meaning this particular system will be entirely stopped, right? It will be at rest. Okay. So this is called as stopping potential. Okay. The minimum potential which you apply to any object in which the current will be turning out zero. When the current is equal to zero, no current will pass. Since no current passes, no electrons will be given out, right? So this entire system will be at rest. Okay? Understood? Three terms. One is your photoelectric effect. A photoelectric effect is important, okay? Like you may get like what is photoelectric effect? Okay? Then threshold frequency and your stopping potential. Okay, then further on, what we will do, like I will do like this particular concepts, like each particular, like if I when I do each particular concept, it has some numericals under that, okay, some problems to be solved. But what happens is what I have observed is suppose if I, finish and the concepts are very small, right? If I finish a particular concept, then I go on to solving problems, then that takes a lot of time. So what I'll do is I will finish, a particular concept and then we will solve the problems all together, okay? So those problems like pertaining to E is equal to H nu are also left, okay, to be solved, numericals. Okay. So next one is Einstein's photoelectric effect. Okay. So under Einstein's photoelectric effect, you'll have this one formula is very important. Okay, kinetic energy. You all know the basic formula for kinetic energy, half m square. Okay. So basically, what is done is this. You can also write in terms of h mu minus h mu dash. Okay. Like this is not important. Okay. Here it is not important. Like how did you get this h and all? Okay. Basically, what he said is kinetic energy is equal to h nu minus h nu dash. Okay. So we can also write this in terms of h. If we take out common, then what will remain is nu minus nu dash. Okay. So this nu we can also write in terms of, if I want to write in terms of wavelength, then what will I do? Right? Okay. C. Basically, it will be C upon lambda minus C upon lambda naught. Okay. But since C is common, both I have taken it out. Okay, so you can one formula written in three forms. Okay, and you all have to know that when I say, okay, if I ask you all a question, okay, which will be the minimum frequency and which will be the maximum? If I see these two terms, which will be minimum and which will be maximum? Second one is minimum, right? So what did I mention in terms of photoelectric effect? Minimum frequency is also called as threshold frequency. So what will be our threshold frequency? Mu dash, mu naught, sorry, not mu dash, mu naught. Okay. So this will be our threshold frequency and this will be our threshold wavelength. Okay. Understood this? Okay. Just write it important. Now going on to Bohr's model of atom. Okay. So basically, what this model explained was it explained the atomic spectra of hydrogen. Okay, probably in your next class, you all will remember, you all will study. Okay, like I will start with the hydrogen spectra. Okay, so basically in Bohr's model, one thing you study the atomic spectra of hydrogen, and secondly is you study the stability of the atom. Okay, so in Bohr's model, two things you study. First is the hydrogen spectra of the atom, and second one is your the stability of the atom, how stable the atom will be. Okay, so for that there are turn two formulas. Okay, just write this. Okay, this basically like how this comes and all that is not like important, but problems are asked. Yes, there will be. Where you have space, right, on your paper down here, where you have Bohr's model of atom, you'll have some space, right? So there you're right, okay? What? I'm not right. This, okay, you're asking me what it is. Okay, no, this is basically Rydberg's constant. What? It's H. Okay. This is basically, okay, for now you'll just write. I thought that I'll write first and then I'll explain, okay? So N can be, like 1, 2, 3, okay? Any whole number. N, basically N1, it refers to which energy level, like E1, E2, E3, like that, okay? So E N is equal to minus RH. This will be the subscript. No, we call it subscript. Down is the subscript, right? Top is the superscript. Yeah. So down, this will be the subscript of R will be H. Okay. Minus RH. Like RH is one entity only. It is not like R is not different and H is not. It is same. Okay. Minus RH bracket 1 upon N square. Okay. Where RH is 2.18 into 10 raised to minus 18 joules. And RH is also called as Rydberg constant. Okay. Rydberg constant. Okay. Rn will be the radius. Okay. Ion, sorry. Then return. So here En is nothing but the energy. The energy of this particular atom will be equal to minus RH multiplied by 1 upon N raised to square. Okay, N square. Okay, where RH will be equal to 2.18 into 10 raised to minus 18 joules, where RH is the Rydberg's constant. Okay, so now this particular formula, right? This is for atom. Okay, mainly hydrogen. Okay, so if you consider hydrogen, then accordingly, like, there are different shells, right? Like hydrogen will have just one shell, right? Because it will be 1s1. So N will be 1. Okay, here. So this is for the hydrogen atom, this particular formula, right? If like further on also, like we will solve, that time you will have like a better picture about this formulas. But when I speak about the atom, right, that is specifically hydrogen, I will use this formula to solve my problems. Okay. But when I consider the ions, okay, like the other ions of say helium, lithium, and beryllium. Okay. If I speak about the ions, then I will use this particular formula, this energy formula. Okay. So basically, there are two formulas. This particular formula is for the hydrogen atom, and this energy formula will be for ions which resemble the hydrogen atom. Like, for example, helium will be basically 2, right? Like 1s2. Okay. Like, suppose if hydrogen will be 1s1, helium will be 1s2. Okay. So, suppose if I write helium plus, that means it will acquire 1s1, just one electron in the s orbital, right? So helium ion, that is helium plus 1, will resemble the hydrogen atom. But it will not be an atom, it will be ion. Okay. Because of the positive charge, it will become an ion. Okay. But it will resemble hydrogen. But only difference is here it is hydrogen atom. Okay. There are no charges. Hydrogen atom in a hole. Okay, here it is hydrogen atom, but here on the contrary, it resembles hydrogen, but the ion forms of the other elements. Okay, so suppose if I have lithium, lithium will be 3, right? Atomic number 3. So 1s2, 2s1. So if I take out 2 electrons, what will I get? 1s1 only. Same way for this. This is 3 plus. So beryllium atomic number will be 4. Okay. You all have no ideas about about the elements, right? So far, you all have studied 1 to 30 till 20. You all have okay. But I was planning to do till zinc. So you all don't like in your higher secondary, you all are not taught 1 till 30, like till 20. It's there. It's told. Ah, okay. You all are telling me what you all had last year. So for last year, you all had like atomic numbers also. Like, okay. Our time, like we do not have, I feel. Okay. So you all will have idea about this, right? Beryllium plus 3 will be nothing but 1s1 only, right? When you remove 3 electrons, just 1 electron will be left, right? So these ions resemble hydrogen, okay? So this formula is specifically for your ions only, okay? And this is nothing but the radius of that particular ion. Okay, if you're told to find the radius, then you can use this formula. Rn is equal to 52.9 into n square upon Z. Z is nothing but your atomic number. Okay? Clear? You all made a note, right? Okay. So now coming on to Bohr's model. Okay. So he basically puts some postulates. What? Mass of theory. A lot of theory. How are you finding this chapter is boring, like compared to the first chapter? Yeah, yeah. This chapter is boring. It is like some students like who like conceptual parts like more, like theoretical concepts and all more than it is like good like for them like to study, I feel. But on the other hand, like those who don't like theory and all much, then but like you'll find it very boring. Like, so your ECM, but for 11th you all have no, you have no option, right? You have to take bio. Okay, so computer science. Okay, so you have that option. Okay. Yeah, I like during our time I studied in presentation, right? So I did not have the option to, like we did not have computer science. And I'm not that great in computers also. So, I wouldn't have taken that as well. Like bio, I like bio, but the thing was in 12, since I had this pressure, like I had no one to drop me for tuitions and all. And tuitions, as you all know, like it consumes a lot of time, right? So if for 11th, I used to go for chemistry and physics and maths. Yeah, like half year I did, and then I did not. I discontinued, like because it was losing like a lot of time and all, and I was not getting much time. Then in 12, I used to go in mornings, like for chemistry and physics, both. I should go. So morning, like the tuitions used to be from 6 to 7:30. So it used to be like a bit tedious and all to get up in the morning, but it would be fine because I would get the rest of my day like to do my work. So I had dropped maths then in 12 because bio and maths it becomes very bulky, right? So like, and like my parents were like, maths and bio, like you see if you'll be able to handle and all. So I thought that, okay, like I'll go for NEET and all, right? So because of that, I thought that maths another headache like to do and maths requires a lot of practice in fact, right? So I said, okay, I'll drop maths. But I still regret till date that I dropped maths in 12. Because the thing is now, like for our masters and for BSc also, we have physical chemistry. Physical chemistry specifically, it deals with all those quantums and all. Like you all will have derivatives and all in maths. I think it is in 12, like sine, cos, and all those things. Like so, those things are important in physical chemistry. So it was a bit difficult for me for masters. So I had to watch videos and learn my 12th maths. So it was like at the end I had to learn maths only. So yeah, so coming on to Bohr's model, okay, he put forward some postulates, okay. So the first one says that electrons revolve around the nucleus in concentric circular paths called orbits situated at a definite distance from the nucleus, okay. This all we know, right? So basically he said that there is something called nucleus and around it will be orbits, okay. And the electrons will revolve around these orbits, okay. So this was the first postulate. Second postulate, he said that there are stationary orbits for electrons. As long as the electrons revolve in this stationary orbits, they do not radiate energy. This energies of electrons remain constant in a stationary orbit. Like, for example, if I don't excite this particular electron, okay, like you all will learn it further on. Like, there is something called as excitation. Like when I supply a particular heat or energy to any electron, it will get excited and it will move to a higher energy state. Higher energy state is nothing but a different orbit altogether. Okay. So whenever, unless and until I supply energy to this particular electron, then only that electron will move, get excited, it will absorb. Basically, when does it get excited? It will absorb that particular energy which I provide to this electron. Okay. Additionally, the energy which I provide to this electron, this particular electron will absorb that energy and it will move to a higher state. Okay. So what Bohr said is, unless and until we don't supply any energy and all, and this is not affected by any factors, it will move in a stationary orbit. Okay. It won't go to some other orbit. It will rather prefer to move around in a stationary orbit. Okay. The third one, different stationary levels or stationary orbits or shells are represented by capital letters K, L, M, N corresponding to the shell number 1, 2, 3, 4. So this is nothing but if I have like K, if I have this particular shell, this will be the K shell, right? Then I will have L, then I will have M, N, so on. So basically, he gave the alphabets to this particular orbits like K, L, M, N corresponding to the shells, like the alphabets. He also gave numbers, like this will be 1, this will be 2, this will be 3. So this you all will also learn, like, you all will have different theories, like the principal quantum number, then the azimuthal quantum number, so on. Okay, so you all will learn that when I speak about numbers, right, 1, 2, 3, 4, those are nothing but the principal quantum number. So each shell will have a principal quantum number, like this particular inner orbit will be 1, next one will be 2, similarly 3, 4, 5, 6, so on. Okay. So basically, he gave alphabets and numbers, okay, to the orbits. Fourth one is, he said that an electron can revolve only in those stationary orbits without giving out energy, for which the angular momentum of an electron is a integral multiple of h upon 2 pi. So basically, he said that angular momentum is nothing but mvr, right? He said that angular momentum will be equal to your h upon 2 pi, okay? And this will be the integral multiple of this particular entity, okay? So he said that angular momentum will be equal to your this, okay? That is h upon 2 pi, okay? Where m will be your mass, v will be your velocity, r will be the radius, okay? M will be mass, v will be your velocity, r will be your radius, and h will be your constant, okay? That is Planck's constant, okay? So fourth one is this. The fifth one is energy goes on increasing as stationary levels, they go further on from the nucleus. So he said that as we go further away from the nucleus, the energy will keep on increasing. This also you all will know. Like, like you all will see that 2s will have higher energy compared to 1s. Okay. So he said that as we go on increasing the orbits, or in other words, as we go further on from the nucleus, it was observed that the energy keeps on increasing. Okay. And the sixth point, he said that energy is absorbed when an electron jumps from lower to a higher energy level. Okay. So now we have two concepts. Okay. Something called as the ground state and something called as the excited state. Okay. Ground state and excited state. Okay. Ground state, when I have any electron in my ground state, the electron will be very happy. Okay. It will be very happy as it will be very like cool. It won't have in other terms. Okay. Like it won't have any stress and all. It will be very happy because it is at ground state. Okay. But when I supply some amount of energy, it will be very like very disturbed, very like unhappy, I can say, okay? As when I supply some energy, it won't be stable at its ground state, okay? Since it will absorb that energy, move to a higher state, that is to the excited state, and here it will be, okay, it will be cool, like that, okay? Like, let's see. In other words, no, I'll give you an example, okay? Like in other words, suppose if I place you in a room, okay, which is a bit like cool, okay, and on the contrary, I tell you to go in some other room where there are no fans, nothing, okay. So it is like that. So when you are in a place when you have fan, when you have AC, you're very stable, right? Like you're cool, like you're happy at that particular space. So same thing happens with the electron when it is at the ground level, right? At the ground state, it is very stable. Okay. But when it gets that energy and it moves to the excited state, it will be unstable. Okay. For some time, okay, like till it moves, it will acquire that energy, move on top to the excited state, and then it will be highly unstable. Okay. Then what it will do is it won't remain here for a longer time. It will tend to give out that particular energy which it has absorbed, and it will come back to the ground state. Okay, so the ground state, if you consider both the ground and the excited state, ground state is a very stable state, right? But why does it move? It will not move on its own. Suppose if I or some other, like say light, interferes in its path, then that particular electron will absorb that particular energy. Because if say at that moment I'm giving some source of energy to that particular electron, it has no option to say that I don't want that particular energy. You take that energy back. It has no option. So it will take that particular energy and it will move to a higher excited state. Okay. Then from the excited state, it will give back that energy which it has absorbed, and it will come down to the ground state, and then it will be stable. Okay. So there are two concepts. Okay. One is absorption. When the electron will absorb the particular energy and move to the excited state, it will be absorption. Okay. And what will be emission? When it will give the amount of energy, okay, be it same amount of energy or in that process, okay, of absorption, some amount of energy may be lost, okay, but emission is nothing but giving out of energy, okay. So you'll have to know that when when the electron moves from ground state to excited state, it will absorb or emit energy, absorb energy. When it comes back to the ground state, it will emit energy, okay. Clear? So basically, like with respect to this parts, right, like absorption and emission, there are two particular spectrums. Okay, one is the emission spectrum, and the other one is the absorption spectrum. So emission spectrum is nothing but the spectrum which is observed when a particular electron will absorb a light or radiation, and it will move to a higher state. Okay, so that is called as the absorption spectrum. Sorry. Okay. So I think behind, right, it speaks about the absorption spectrum. Okay. So that is nothing but when I apply or when I give a source of light to any object or electron, it will absorb the energy and move to a higher state. Okay. So it is said that the line spectrum of the substance which is formed, okay, will contain some black lines, okay? Like it will appear like suppose when it takes that particular energy and it will absorb the spectra which you get, right? It will contain some black lines in it. Okay, this you all will learn like in depth. Okay, but for now, you'll have to have a brief idea. Key absorption spectra is what? The spectra which you get when you absorb a particular energy. Okay, and the spectra which is obtained right after absorbing will contain some black lines. Okay, this is the absorption spectra. Coming on to the emission spectra is nothing but when you emit light, okay? When the electron is at a higher state and when it wants to give back the electrons and come back to a normal or a stable state, okay, it will give out light, right? When it gives out light, that particular spectrum is called like the emission spectrum, okay? Emission spectrum can be of two types, that is continuous spectrum and line spectrum or atomic spectrum. Okay, so what is the difference between continuous spectrum and your atomic spectrum? The only difference is when we say continuous spectrum, right? The light which is emitted, right, or the spectrum which is obtained in continuous spectrum, it will be continuous, like it will be a white light. Okay, so white light normally will comprise of your seven colors, right? Be pure. Okay, so basically, continuous spectrum is when you get that light in a continuous fashion, as in you get the white light where there are no black lines. Okay, in other words, no black zones. Okay, it will be continuous, like you will get the white light. Okay, but when I speak about the atomic spectrum, it will be the emission spectrum, okay, like which is the spectrum which is obtained after giving out energy. But in this, you will observe like some dark zones, okay, like you will get some colors, okay, you will get some colors, right? And in between those colors, right, there will be a dark zone, like some black lines, okay. So that is called as your atomic spectrum. In continuous, there won't be this black lines. It will be a continuous colored part, okay, like a color spectrum, which you'll get like different colors. But in your atomic spectrum, you will observe like, you will get colors, no doubt. But in between those colors, you will get some dark zones or some black lines. Okay. But like why you get those and all that to that depth you all don't have, you all just have to remember these terms. Okay. For now. Clear? Any doubts? Okay. So hydrogen spectrum, probably I'll do it in our next class. But for now, like since we still have time, right? So you all can we'll solve some numericals. Okay. Seventh and eighth one I said homework, right? Let's go on to solving the ninth one. You all are told when are your exams and all, everything. 20th July. Okay. But like, how's the progress going? Like, the completion of the chapters and all. You also, Rosie. So here, you and you both. Now they have changed the uniform. This was from first only. So, like, meaning we are still on the first chapter, and then maybe they will take some extra classes and all, and they'll accommodate. So, every Tuesdays. Okay. So, what you will be? Okay. Okay. So, try solving question 9. Okay. So, what does it say? We have to calculate the energy of 1 mole of photon of radiation whose frequency is 5 into 10 raised to 14 hertz. Okay. So what are we given? We are given frequency, which is 5 into 10 raised to 14 hertz. Okay. And what are we told to calculate? Energy of, to be more specific, they have said to calculate the energy of 1 mole of photon. Okay. So which formula will we use? Here we want the energy, okay, of the photon. So which formula? So far we have come across 4, right? So which from the 4 will use? Hmm? E is equal to h mu. Okay. So E will be this H will be probably, you know, in your question, like H will be provided, okay, at the start of your question paper or the question where you're given this particular concept, okay? 10 raised to minus 34 joules second. So H will be 6.626 into 10 raised to minus 34 joules second multiplied by 5 into 10 raised to 14 hertz. I can also write in terms of second inverse. Okay. So if I calculate this particular answer, okay, just calculate and let me know. Okay. Thirty 3.1. Okay. So suppose if I want to write, okay, you can keep this also, or you can also write 3.31 to 10 raised to, when I move towards the left, it will be 3.31 into 10 raised to, what will be the units for this? Calculate. Because of that, in order, like, you know, like it becomes very difficult at times because normally it is joules only, but to be more specific, when you solve, right, you all can take like, you know, the units which are mentioned here and then multiply that. Like when you multiply the numbers, take those also. Like here I have taken joule second because H is joule second into hertz I have converted to second inverse. Okay. So this and this will cancel out, right? Like plus 1 minus 1. Okay. So how much will I get? So joules. Okay. But now here they have asked more specifically, they have asked energy of 1 mole of photon. So what do we know? Like 1 mole is equal to Avogadro's number, right? 6.0. Energy for 1 mole of photon will be equal to your 3.31 into 10 raised to minus 6.023 into 10 raised to 2, 2 also you can take some, they take 2, 3 also. Okay. 10 raised to 23. The units will be mole inverse. Okay. So accordingly, if you multiply, then the answer will, you will get 19.5. 95 into 10 raised to 4 joules per mole. Okay. Then try solving the 10th one. Okay, so what does the question say? A 100-watt bulb emits monochromatic light of wavelength 400 nanometers. Okay, it says to calculate the number of photons emitted per second by the bulb. So we are given the power. Okay, so this is question 10. We are given power of the bulb, which is 100 watts. Okay. Okay, now watts you can also write in terms of joules per second. So I will write 100 joules second inverse. Okay. Now they have told us to calculate the number of photons, okay, emitted per second by the bulb. Okay, so for that, to find the number of photons, we have to find how much of energy it is required, right, to emit. So for that, we will use this formula. E is equal to h nu. Okay, and we'll find out the energy. Okay, we are given the power. Okay, and we are given the wavelength, right? And we are told to calculate the number of photons which will be emitted per second. So what we will do, we will find the energy of for one photon. Okay, this particular energy like wavelength. Huh? This is basically power of the bulb. The power of the bulb they have given. So what we have to do is we have to find the energy for one photon. Okay. So basically when we find the energy for one photon, we can take the power and divide it with the one energy, right? So when we divide anything, when we have something, say, suppose if we have, we can say like 6 mangoes, okay, and I find like the cost for say it is like I have some particular area, okay, I have something large, okay, and if I know the cost of one particular amount, like say any object or say fruit, then will I not able to find like like how many mangoes I get for that particular price? You're getting me? Okay, like in simpler words, if I know the cost of, okay, suppose if I know some cost, okay, some amount, okay, and I pay, and that is 600, okay, but I also know the one cost, okay, like the one item cost of this particular thing. Will I not be able to find how many items I get? Understanding, right? I know the total cost and I know the one object cost. Now I want to find how many items will I get for that particular cost in that budget of mine or the amount which I paid. Simple as that, right? So here also it is the same thing. Okay. Like they have given us power. Okay. Power not of one. Power is like general they have given. Okay. and we will find the energy of one photon. Okay, so what we will do is we will divide power upon the one energy photon energy. Okay, so when I do that, I will get like the number of photons which will be given out for that particular power. Okay, simple as that, right? Any doubts? Understood? Okay, so how will I find wavelength? So it will be C upon lambda. So it will be 6 point, yeah, 6 points. This time you are right. 6, 6.62 minus 34 joule second into 3 meter second upon this will be 400 to 10 raised to minus 9 meters. Okay. So this meter will get cancelled. Plus 1 minus 1 will get cancelled. So what answer you all will get? You all will get, basically you all can do it at home, okay? 4.969 into 10 raised to minus 19 joules. Okay? So basically this will be nothing but energy of one photon. Okay? So the number of photons, number of photons emitted will be 100 joule second inverse upon 4.969 into 10 raised to minus 19 joules. Okay, so you will get the answer is 2.012 into 10 raised to 20 second inverse. Okay, why second inverse? Because this joule and this joule will get cancelled. Okay. Only like I feel only 11 and 12, like, you'll have to struggle with the calculation part because you all have to use logbooks, right? But from your bachelor to like further on after your higher secondary, after you're done with your 11, 12, then it is like you can use scientific calculators and all. Only for 11th and 12th, like you have this issue.